In this video, we're going over the concepts of Chapter 5, which is titled Heating and Changes of State, a Story of Polarity and Intermolecular Forces. In the previous chapter, we learned about Lewis structures. And when it comes to polarity, we need to understand that first we must explore VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. VSEPR theory, it's based on mutual repulsion of electron pairs around a central atom, and it is used to predict the molecular shapes of molecules. In reality, all the atoms that are present in a covalent compound are going to have electrons, and they're all connected to a central atom, as we observed previously. Due to the charge of electrons, and since they are surrounding that central atom, those negative electrons will like to stay away from each other. And that's what helped these molecules to adopt certain geometries. When we're looking at this concept, we must understand and learn what is an electron domain group. An electron domain group is just an illustration of electrons in a molecule. Electron domain groups include lone pairs, single bonds, double bonds, or triple bonds. Each one of these categories constitutes one electron domain or group because it is a way in which we represent electrons. In figure 5.2, we have the use of balloons to actually represent the clouds that electrons form around the central atom. So when we rationalize these different shapes, we can assume specifically that the central atom is here. And then in this molecule, we have two atoms on either side. On B, this is going to be where the central atom is, and then you have three different domains around it. And lastly, it is a little bit hard to see, but you can imagine that in the middle of those four balloons, we're going to have our central atom, and it is surrounded by four electron clouds. There are some basic rules when it comes to electron domains. It is important to know that all valence shell pair electrons around a central atom are counted equally, meaning they represent one group, regardless of how they look. Meaning, a lone pair counts as a group, a single bond counts as one group, a double bond counts as one group, or a triple bond counts as one group. We can see that this is what is stated in rule number 2. Single, double, triple are all considered a single electron domain, meaning a single representation of electrons. In order to go over this concept, I'm going to now move to slide 7. Where here I have different drawn Lewis structures, and we can actually count the electron domains or electron groups around the central atom. I'm going to do all the examples that we have on slide 7. As we can observe, in the molecule carbon dioxide, CO2, my carbon atom has a double bond and a double bond. That means that it has two electron domains. I'm now going to look at formaldehyde. My carbon atom has 3 electron domains, a double bond, a single bond, and a single bond. Next, I have ammonia, NH3. Nitrogen has four electron domains, a lone pair, single bond, single bond, single bond. And lastly, I have water. Water around the oxygen atom has four electron domains, lone pair, single bond, lone pair, single bond. With this information, now we can actually see the geometries that comes from VSEPR theory. We can see that once we have determined how many electron groups or electron domains are around our central atom, then we can refer back to table 5.1 to look at specifically the electron domain geometry, molecular geometry, bond angle for any specific covalent compound. The electron domain geometry is the general shape that a molecule assumes when repulsions are minimized between electron domains. Molecular geometry, which is also known as molecular shape, is the three-dimensional shape of bonded atoms in a molecule. The first one we're going to explore is when your central atom has two electron domains. As we can see in this zoomed in image of table 5.1, when a molecule has two electron domains, the electron domain geometry is linear. Many of the molecules that are linear are going to have two electron domains in non-bonding domains. Remember that a non-bonding domain is another word for lone pairs. When it comes to its molecular geometry, is going to be linear. And the angle that separates the central atom to the atom that is next door is going to be 180 degrees. Now let's look at geometries, specifically when there are three electron domains in a molecule. If the central atom is surrounded by three electron domains, then the electron domain geometry is called trigonal planar. When it comes to the molecular geometry, then we have two variations. A molecule that has around the central atom three electron domains and no lone pairs, its molecular geometry is also called trigonal planar. The bond angle that it is separating the atoms, meaning this angle, is 120 degrees. If you have three electron domains, but then the central atom has two bonded atoms and a lone pair, then the molecular geometry is called bent. And we can observe that the angle for that molecule is less than 120 degrees. That means that because in this molecule, we have an electron cloud due to the lone pair, that is going to reduce the bond angle that is going to be between the central atom and the atoms that are connected to it. Lastly, we have the VSEPR rules for when a molecule has 4 electron domains. Any molecule that has 4 electron domains is going to have an electron domain geometry that is called tetrahedral. When it comes to tetrahedral molecules, if the central atom has 4 bonded atoms and no lone pairs, then the molecular geometry is also tetrahedral. The angles present in the molecule are going to be 109.5 degrees. Tetrahedral molecules can also have 3 bonded atoms and 1 lone pair on the central atom. When that's the case, the molecular geometry is called trigonal pyramidal. And understand that that is going to still have an electron domain geometry of tetrahedral. The only thing that changes is the molecular geometry. For molecules like this, then because there is a lone pair on the central atom, then the angle that is separating these atoms is going to be less than 109.5 degrees. Lastly, for a molecule that has 4 electron domains, but then around the central atom, we have 2 bonded atoms and 2 lone pairs, the molecular geometry is called bent. And the bond angle also is going to be less than 109.5 degrees because now we have 2 electron clouds that are going to reduce the angle between the atoms. Let's apply all of this information to the molecules that we have in slide 7. Let's get started with specifically CO2, and we're going to do all the examples in the slide. We already observed that CO2 has 2 electron domains. And if we go back in the slides, specifically we go back to slide 4, we can observe that molecules that have 2 electron domains have an electron domain geometry and a molecular geometry that it is linear. So the answer here is linear. And linear, the angle that is present between the central atom and either side of the atoms that are connected to it is going to be 180 degrees. The question doesn't require it, but I want to remind you of that measurement. Let's now look at formaldehyde. Formaldehyde, specifically in its Lewis structure, is going to have 3 electron domains. We can observe that around the central atom, we have only bonded atoms. If we go back to the information that we have on slide 5, a central atom that does not have lone pairs means that its electron group geometry or electron domain geometry is going to be trigonal, planar, and the molecular geometry is also trigonal, planar. Let's now do the example on letter C, which is ammonia. Ammonia has 4 electron domains, just like water. And when you have 4 electron domains, if you go back to slide 6, you can see that in ammonia, since we have 4 electron domains, anything that has 4 electron domains has an electron domain geometry that is called tetrahedral. The molecular geometry Is going to depend on the bonded atoms and if there's lone pairs on the central atom. In this case, because ammonia has one lone pair and three bonded atoms, the molecular geometry is going to be trigonal, pyramidal. Lastly, we have on letter D the example of water. Water, just like ammonia, has 4 electron domains around the central atom. So this means that water is a tetrahedral molecule. Because the central atom has 2 lone pairs and 2 bonded atoms, the molecular geometry is going to be bent. Let me now include the angle degrees for each one of those molecules. On letter B, because we have a trigonal planar molecule, the atoms are separated by 120 degrees. In ammonia and water, because they are tetrahedral, and due to the lone pairs that are on the central atom, both of them are going to be less than 109.5 degrees.